Okay, so we were talking about what a definite integral was. And a definite integral is basically just the shorthand version of saying that I'm going to add these rectangles together and I'm going to take the limit as n goes to infinity. So it's just a terminology kind of thing. So we were on this page. So we said that the definite integral, which uses the same terminology as the indefinite integral, except that it has these numbers, this number a, which is the lower limit of the integration, and b, which is the upper limit of the integration. Now at this point officially we still don't know that you can use the integration, the antiderivative, and then evaluate the antiderivative to figure out the area. I've just demonstrated that it works, but officially we don't know. So in the homework for this section, when you see this, it doesn't mean to do it the easy way, it means to do it the hard way, which means that, so I'll show you in a second, but a lot of people in this section will use the easy way to calculate the area underneath the curve, and that's not the intent. So if we saw this, we'd say this is the integral of f of x from integrating from a to b, where it's x equals a and x equals b. So again, to emphasize it, when you see something like this, the integral of x squared dx without the limits, that's what's called an indefinite integral. And what you do is you take the antiderivative and you include your arbitrary constant c. So you end up with an equation. This is called the general solution to the original f prime of x was equal to x squared. And then f of x would be equal to x cubed over 3. The definite integral has the limits, and what that means is find the area underneath the curve x squared between x equals 1 and x equals 6, and you end up getting a number. And if you actually go online and search for those two, using those two terms, so if you put in indefinite integral calculator, what you'll end up with is something like this. So you see an integral sign. And so if I want to do the integral of x squared like that, and I say go, what it does is it shows you how to do the integral. And the result is the answer's here, x cubed over 3 plus c. So it's and it shows you the steps. So I'm not encouraging you to use this to do your homework unless you get stuck. And you have the solutions anyway. But if you wanted to, if you wanted to try some different, if you're like, I'm still not getting this, let me pick a problem out of the book, and you say, okay, I do it, but I don't get the right answer, then it's probably acceptable to go to online to just see what they show as the steps, because they're showing first you apply the power rule and you add 1 to the exponent, divide by the new exponent, and you simplify, and then you add the arbitrary constant to the solution. Actually, I would have added it here, but that's what an indefinite integral calculator does for you. If we go back and we put in definite integral calculator, so there's the definite integral calculator, and you'll notice it has little boxes. So if I put in x squared and I put the integral from 1 to, and yeah, something's happened here. Let's redo this. I guess they want you to put the limits in first. Okay, so I'm going to put the limits in first. So from 1 to 4 of, and then you can put your function in here, x squared. Well, let's actually do it from 0 to 10, because that's what we've done in class, 0 to 10. and you integrate it, go, we should get 333. So it gives you the answer, 1,000 over 3. And it shows you the steps to do the calculation. But at this point, here they calculate the indefinite integral, but when we get to section 4, you'll see that what they're doing is they're evaluating this at the upper limit, and then this is the lower limit, and subtracting. The arbitrary constant cancels out, so you don't have to worry about it. Anyway, that's a little sidelight. So again, equation, number. Okay, here's just a theorem which says that continuity implies integrability. So it says if a function is continuous on a closed interval from x equals a to x equals b, you can also integrate it. If it's not continuous, like there's a vertical asymptote or there's a hole, you can't. It's not continuous, and you can't integrate it. We'll find out you can integrate up to the discontinuity, but you can't integrate through the discontinuity. And this is what I've already talked about. The definite integral is the area underneath a curve. So this says if f is continuous, which means it's integrable, and non-negative, which means that it's above the x-axis. So if the function is continuous and non-negative on a closed interval, which means it includes the endpoints, then the area of the region bounded by the graph of f, so that's the curve that bounds the top of the area, the x-axis which bounds the bottom of the area, and then the two vertical lines which bound the left and right-hand sides of the area, that the area is represented or is calculated by doing the definite integral. So it's kind of reiterating what we said earlier. We said this was equal to the summation from, or taking the limit is n goes to infinity of the summation of I equals 1 to n of f of x sub I times dx, which is the area using the limiting process. So what does this say? Up to this point, the indefinite integral represents the antiderivative, and the definite integral represents the area underneath the curve. Okay, we already talked about that. Okay, let's see what else there is in this section. Okay, I'm just checking out what I have to talk about here. Okay, so there are kind of some theorems that apply to definite integrals relative to area. So this is just to demonstrate one concept. If I were to use the limit definition for, well, actually, I'm not sure if I wait a second. What happened there? Something happened yesterday and it stopped recording. It's still recording. Okay. I was worried yesterday's class didn't record, so I'm going to have to redo it. Okay, we'll find in section 4 that if we take the definite integral from negative pi to positive pi of the sine of x, we get 0. So what happens, this is the sine of x between x equals negative pi, which is this value of x, and x equals positive pi, which is this. And it goes below the x-axis for the first half, and it goes above the x-axis. And this definition over here says that the function must be non-negative. So theoretically, we could only use the definite integral for this part of the curve using that definition. We'll find out later that's not exactly true. Because what ends up happening is if the curve is above the x-axis, then the integral, the area is positive. But if the curve is below the x-axis, you'll get a negative area. So you'll get the same magnitude because these are symmetric. So you'd expect them to be, the values to be the same. But the actual definite integral can be turns out can be either positive or negative. And the reason the integral from pi to negative pi to positive pi is 0 because this area is negative and this area is positive, and when you add them together you get 0. So it doesn't mean nothing's happening. It doesn't mean you just got a flat line, which also, if you just had the x-axis, there would be 0 area. But in this case, there's positive area from 0 to pi, and there's negative area from negative pi to 0. Now, it turns out if you do the antiderivative operation, if you change the limits, so instead of integrating from 0 to pi, you integrate from pi to 0. So you'll notice here I go from 0 to pi, here I go from pi to 0. What that does, by integrating in the opposite direction, you change the sign. So integrating from here to here is positive, integrating from the other way is negative. So if I integrated from 0 to negative pi here, I would actually get a positive area. So that's what that's saying. So if I integrate from negative pi to 0, this area would be negative. If I integrate from, and also from symmetry, you can see here that the integral from negative pi to 0, which is this, is just the negative of the area from 0 to pi, because this one's positive and that one's negative. Okay, so here are a couple of things. If the limits are the same, if you have a definite integral from x equals a to x equals a, the answer is 0, and that's because you basically, if the limit wasn't the same in the upper and lower limits, but they approached each other, your area is going to get smaller and smaller and smaller because this dimension is going to get smaller, and when they actually equal each other, then the area is 0. It's kind of like saying the width of the area of a rectangle with a side that has 0 length is 0. Okay, seems kind of obvious, but you got to cover these things. What we just talked about is if f is integrable on a to b, then if we change the order of the integration, if we integrate from a to b and we get an answer, we'll get negative that answer if we integrate from b to a. Switching the limits changes the sign of the result. It doesn't change the magnitude, it just changes it from positive to negative. And we'll find out that there are, you're like, why would I integrate from a bigger number to a smaller number? And we'll find out in chapter 8 where that happens. We're going to make some transformations where the initial limits of integration go from a smaller number to a bigger number, but when we transform it, it's going to go from a bigger number to a smaller number. So. And the additive property basically says that if you have a curve, a function, from a to b, and you pick some intermediate value c, if you find the area from a to c, and you add it to the area from c to b, that it's equal to the total area between a and b. Again, it seems pretty obvious visually. If you take something, you break it up into two parts, the sum of the individual parts is equal to the sum of the total parts. If I took a piece of wood and I cut it in 1/3 and 2/3, if I weigh the individual parts, it's going to weigh the same as the original total part. So the same thing applies for integrals. So if you want to break up your integral into two parts, that's fine for whatever reason. It's not going to change the answer. So that's called the additive interval property. This one makes sense. This one makes sense. This one's not quite as obvious, but it's true. And what else do we do? Okay, here's some more properties. We had some properties associated with indefinite integrals. This basically says that if you have a constant times a function and you want to find the area underneath the curve, like say 3x squared, that's the same as 3 times the integral of x squared. So all a constant does in front of a function is just increase the area by that factor. So let me erase this little bit right here. I'll give an example of what I just said. Let me turn my thing off here so it doesn't beep. So what this as an example is, the integral from 0 to 10 of 3x squared dx is equal to the integral from 3 times the integral from 0 to 10 of x squared. Only the variable part do we have to integrate. The constant part, what we do is we say we can take that outside of the integral. So then we can say, oh, we just have a x to the n. I add 1 to that, to the exponent, and use the formula. The formula may not say 3x squared or 3x to the n, so you can move the 3 out, so it just becomes plain x to the n kind of thing. This one just says if you have a function that's made of two parts that are added together, you can take the definite integral of the first part of the function and add that or subtract that, depending upon what you have here, to the integral of the second part of the function. So let me give you an example of that one. So let's say h of x equals 3x squared. Well, let's not use 3. Let's just leave it without a constant for right now. Let's say it's x squared plus x cubed. So what you could say is if you wanted to find the integral of x squared plus x cubed dx from 1 to 5, that's the same as the integral from 1 to 5 of x squared dx plus the integral from 1 to 5 of x cubed dx. So, we have a formula for doing this and we have a formula for doing that. So we can take the in this case, not the antiderivative, we find the area. So if you have this combined function, you can find the area into this function and the area into this function and add the two areas together and you get the total area. That's basically what's going on there. Again, that makes sense. This makes sense from derivatives. The constant, when we took a derivative, the constant just kind of hung around until we had multiplied it out to simplify it. So the same way applies here. You can take the integral, the constant outside. And again here. Now what doesn't work is if you had a product. If you had f of x times g of x, it's not, it's just like the product rule for derivatives. It's not so simple. When you add stuff or subtract stuff, it's simple to deal with it. When you have products, not so easy. We'll have to wait till chapter 8 to figure that one out. And what else have we got here? Preservation of inequality. Don't even write this down, just pay attention. So if f is integrable and non-negative on the closed interval a to b, and if this is greater, what are they saying here? If it is integrable, non-negative. So what this says is basically if the function is above the x-axis, then you get a positive area. Okay? That's what that means, since it says non-negative. And that makes sense too. If you have a curve that's above the x-axis and you find the area, it's going to be a positive value because it is a positive area. The second one says if two functions are integrable on the closed interval and f of x is always less than g of x for every x in the interval, then the definite integral of f of x, which is the area, is going to be less than the area under g of x. And again, that makes sense. Here's f of x. It's always less than g of x, and the area under the red curve is going to be less than the area under the blue curve. Nothing surprising there. Okay, so there's your homework for section 3. And because we don't know how to do we don't know how to use the fundamental theorem of calculus, this is just more practice at using the summation stuff. So you want to evaluate these all by taking the limit as n goes to infinity of the summation from I equals 1 to n of f of x sub I times delta x. Okay, don't do the easy way. Don't do the easy way yet. Once we get to section 4, you won't have to do the hard way anymore. You just have to do the easy way. So you're all looking confused.
Not at all.
Oh.
Completely with you.
No, I mean, where Lexi's gone.
I don't know.
I don't know.
I think she forgot something in her car, actually.
Oh, is that what it is? Oh, okay. Okay, she's like. Yeah. Okay. Yeah, she doesn't usually do that, so what's going on? Oh, she's back again. You're back. That was a quick trip. Oh, you had somebody's backpack or something. So. She was trying to get by with that, subtly doing whatever that was. Because I saw your stuff there, and like she's not leaving. You had what?
Okay, here's the full story. Okay, so I'm on my way to Bath County because I'm meeting someone, and I'm meeting Senator Deeds, and I'm 40 minutes late.
Uh-oh.
So I'm driving fast, and I'm about to run out of gas. So I ran out of gas right in his parking lot, and I call Mom. I'm like, Mom, I need you to bring me some gas, and I need a lot of it. So she brings me a jug of gas, and she put the jug in my car, and now everything in my
Smells
car
like gas. Yeah.
Lexi's making sure everyone does not get high.
Is that what it is? Okay. Yeah. Yeah, I didn't smell it. Do you guys smell the gas?
I was like, I'm doing a sore throat. Lexi.
So is your backpack.
Yeah, but I need to know how to get rid of it.
How to get rid of the smell.
Anyone knows? Just take everything out and put it in the wash. How do I get it in my car?
Yeah.
Take it to the car wash and open the
Well, since you didn't spill any, it should just dissipate after a while.
I took it out yesterday.
Yeah.
I didn't spill it.
Because gasoline's pretty volatile, so it should just vaporize a certain. But it also that's why you feel kind of woo. Okay, so before we move on to section 4, let's go ahead and pull out the handout that I gave you guys the other day that we haven't completed yet. So section 4 is the fundamental theorem of calculus, which we've already introduced informally. Okay. So here it is. The fundamental theorem of calculus says if a function is continuous on a closed interval a to b and capital F is an antiderivative of f on the interval a to b, then the definite integral from a to b of f of x dx equals the antiderivative evaluated at the upper limit minus the antiderivative evaluated at the lower limit. So I'm going to just write out some. This basically says the area underneath the curve defined by the function f of x, the x-axis, and x equals a and x equals b. Okay, so that's the area, is equal to the antiderivative of f of x evaluated at x equals b minus the antiderivative of f of x evaluated at x equals a. Okay, so that's what the formula is basically telling us. So it means that now, from now on, once you finish your homework for section 3, to find the area between a curve and the x-axis and the vertical lines x equals a and x equals b, all we have to do is take the antiderivative of f of x and evaluate the antiderivative at the upper limit and subtract the antiderivative of the lower limit, which is a lot easier than doing it the long way. So, thinking back to what we did, one of the problems that we did was finding the area under the curve f of x equals x squared between the values of x equals 0 and the value x equals 10. And we came out with an answer using the limit definition. The answer was 333. So we've already done this, but just to reiterate it, instead of doing that long limit definition, what we can say is that the area underneath the curve x squared between x equals 0 and x equals 2, so that's what that says. It's a definite integral, which means it's an area. What we do is we take the antiderivative of x squared. So the antiderivative of x squared is x cubed divided by 3. And we put this vertical line. What the vertical line is kind of an intermediate step to say, first we're going to take the antiderivative. So first we find out what capital F of x is. And then the next step is we then plug in these to evaluate the antiderivative at the upper limit minus the antiderivative at the lower limit. So what we'll have is 10 cubed over 3, that's this part, minus 0 cubed over 3, that's that part. And then you just evaluate it and you get 1,000 divided by 3, which is 333.3333. So there's a couple of things to notice. One thing about if you look at the definition, it says, if a function f is continuous on the closed interval, and the reason they say that is because if it's continuous, then it's integrable. Okay? So if it's continuous and f is an, okay, it says an, not the antiderivative. So it can be any of the antiderivatives. Well, the only difference between the antiderivatives is the arbitrary constant c. So you'll notice that we don't have the arbitrary constant c in anymore, and that's because no matter what the arbitrary constant is, it cancels out because you're going to have the constant c here when you evaluated the upper limit, and you're going to have the constant c here when you evaluated the lower limit, and you'll have this minus that, and it disappears. So you could say the antiderivative we use is the one that doesn't has c equals 0. because it doesn't matter. It's the difference between the two. It's just like potential energy in physics. It doesn't matter what the actual values are. It matters what the difference in the values are. So where we define it, y equals 0 is immaterial, just as long as they're consistent. And so the same thing kind of applies here. It's the difference in the function which is important, and therefore that where we set c equal to doesn't matter. So don't ever put an arbitrary constant c here. You don't need it. It's going to cancel out. Also, this vertical line, you always want to put that there to do the two steps. You don't want to just go from here to there, because you need to do the antiderivative part first, but you don't want to just forget about what these, you don't want to lose the information about what limits I'm evaluating it at. So we use this vertical line just kind of to keep them in our mind so we know what to do in the next step. So no arbitrary constant, take the antiderivative, evaluate, add the upper and lower limits, and then you get the area underneath the curve. So let me just see what else I've got to talk about here. There's not a whole lot left to do except just do some examples. I'm just seeing what the, okay, yeah. Okay, right. So I've got a handout that